Everyone, welcome back to 3 Deviations. In today's video, I would like to focus on the shell method. So this is the second method of finding volumes of solids of revolution. So solid of revolution is where we take a region and we rotate it around an axis. In the last pair of videos, what we did is we talked about taking regions and rotating them around axes, like the square root of x. We would take that around axes like that, and we would use little disks. We'd use little disks to determine the volume, and then we would add those disks up, and that would give us an accurate volume when we took it at the limited case, which became a volume or a area integral that we rotated about the axis. Now we're going to be moving into the second of the two methods of finding volume, and this is the shell method, so the method of cylindrical shells. So in this method, what we do is we take something, and again, this could be on the y or x-axis. We've been doing a lot of stuff on the x-axis, so I'm going to draw it on the y-axis right now. But we take something that looks, I don't know, maybe a function like this, and we'd rotate this around the y-axis. So you'd want to find the volume of this kind of weird cone shape thing. And to do that, instead of using that disk method, we use a shell method. This shell method basically says that we take cylindrical shells and we add them up. So if maybe I have a cylindrical shell here, this is my first shell, and that's also here. So this kind of goes around here. And this is a little cylindrical shell that we've got going around the thing. And then we have more of those going in, like concentric little cylindrical shells that we add up in our region, and that will give us an accurate volume, and that's going to be a lot easier for these types of functions than the shell method. So let's give this a try. To do this, I want to make a derivation, and we're going to save examples for later videos. So this derivation, we're going to consider the volume of a cylindrical shell as the difference of volumes. Okay, so let's look at a cylinder, and yeah, let's look at a cylinder first. Here's our cylinder, and I want to find a cylindrical shell. So a cylindrical shell is really a cylinder with another cylinder inside it that's hollow. So if I look at a cross section of a cylindrical shell, it looks like this. Here's my cross section. This is a bird's eye view of my cylindrical shell. This all in here is solid, and we have a little radius in here, and that is the radius of the outer shell minus the radius of the inner shell. So if I'm in here, and this region and all the dots is my inner shell, or my inner cylinder, and this is the outer cylinder, then I have a radius of my inner cylinder, then I have a radius of my outer cylinder, then the radius of my cylindrical shell is going to be the difference, right? So let's take a look at this derivation. So we are going to say that the difference in the volumes of the cylinder is pi r squared, pi r2 squared of h. So let's call, instead of, let's say that the outer radius is equal to r2 and the inner radius is equal to r1. Okay, so we have pi r sub 2 squared h minus pi r sub 1 squared h. And we can factor that, and that becomes pi h times r sub 2 squared minus r sub 1 squared. All right, now we can do a little bit more work with this, and this is going to end up being, we'll factor that binomial there. It will give us pi h times r sub 2 plus r sub 1 times r sub 2 minus r sub 1. We can further rewrite this, and you'll see why we're going to rewrite this like this, but we're going to get that to 2 pi h times r sub 2 plus r sub 1 over 2 times r sub 2 minus r sub 1. Okay, now let's make a couple of definitions. So we're going to set our radius equal to 1/2. So this is in our cylindrical shell. We set our radius equal to the average of r sub 1 and r sub 2. And then we set our delta r equal to r sub 2 minus r sub 1. Okay, so now what we do here is we rewrite our formula, and that's going to give us the volume equals 2 pi r times h times delta r. All right, now this is starting to look like something that we could put into an integral. So let's imagine that we're dealing with a function here. So our radius is going to be our x value. So our radius is saying how far away is our function away. And then our height is our f of x value. How high is the function off of the ground, so to speak, but I really mean the x-axis or whatever axis we're integrating across. And now I bet you can already see this coming. We are going to get a Riemann sum that turns into an integral. So that gives us the volume equal to the limit as n approaches infinity of the sum from I equals 1 to n of 2 pi x sub I f of x sub I times delta x, and that implies that the volume is equal to the integral from a to b of 2 pi x times f of x dx. All right, so again, this is some pretty abstract stuff. We just dealt with a derivation that didn't really show us many examples, but don't worry, we will be doing many videos on this more challenging method of finding volumes. So look out for those, and we will get started with that in the next video. Thanks for watching. See you next time.